Let's solve the equation 2 to the 3x plus 1 equals 16 to the 5x minus 1. Now, it'll be convenient because of the very similar bases to change the 16 into a 2 to the 4th. Please don't change 2 into 2 to the 4th. That would change the problem. Change 16 into 2 to the 4th. And then before doing anything else, let's clean up the right side. So we have this rule about base to an exponent, quantity raised to an exponent. So you get to multiply the exponents. That's why here, now you see 2 raised to, now the exponent is 4 times 5x minus 1. Now that you have base to an exponent on the left side, you have base to an exponent on the right side. Because the bases are the same, we can now set the exponents equal without slashes here. So I have 3x plus 1 equals 4 times the quantity 5x minus 1. Now that's a nice equation. We could, for instance, distribute the 4 on the left side, 20x minus 4. The left side is still as it was, 3x plus 1. Now we can subtract 3x on both sides, add 4 to both sides, and have 5 equals 17x. Divide both sides by 17, and you have 5/17 equals x. We're done. You could, of course, work on checking your answer if you like, but we don't actually, strictly speaking, have to check our answer because the original equation did not have logarithms. Just comment again. We went from this line here, 2 to the 3x plus 1 equals 2 to the 4 times quantity 5x minus 1. We went from that to one line below, 3x plus 1 equals 4 times quantity 5x minus 1 because both sides said 2 to the something. Let's take a look at solving 7 to the 5x minus 3 equals 4. Now we have to use the definitional logarithm. Okay, so 7 to the power 5x minus 3 equals 4 turns into 5x minus 3 equals log base 7 of 4. Of course, if you have the two sides of the equation swapped here for your first line of the answer, that's fine. So if you have log base 7 of 4 equals 5x minus 3, that's okay. Let's add 3 to both sides. Note that when you do that, you'll have 5x equals log base 7 of 4, then a plus a 3. So you don't have log base 7 of 7. There's no 4 plus 3 going on in the problem here. Now divide both sides by 5, and so you have x equals log base 7 of 4 plus a 3 all over 5. Now the right side wasn't 7 to the something, right? We had just the plain old number 4, right? We had just a constant, just the constant 4. That's why we had to use the definitional logarithm, because there was a constant on the right side. Okay, the definition of the logarithm was helpful because one side of the equation 7 to the 5x minus 3 equals 4 was a constant. Which side? Well, the right side was just a constant, was just the constant 4. Now let's solve log base 3 of 8 minus x equals 2. Well, same sort of deal here. One side of the equation is just a constant. So we'll use the definitional logarithm and have 3 to the second is equal to 8 minus x. Now there's actually not a lot to do to solve for x. We can simplify the left side, which says 3 to the second, into just the number 9. So 9 is equal to 8 minus x. We can add x to both sides, subtract 9 from both sides, and you'll have x equals 8 minus 9. And if we simplify the right side, we have x equals negative 1. Now we're not technically done because this time the original equation had logs. So we need to check if x equals negative 1 is a solution. The input to the logarithm here, the input to this log function is 8 minus x, and we want 8 minus x to be positive. We hope that 8 minus x is positive, so let's take a look at 8 minus x, plug in the negative 1 for x, and we have 8 minus negative 1, which is, in other words, 8 plus 1, which is the number 9, and that number 9 is positive. That's good. So x equals negative 1 is, in fact, a solution. It doesn't matter that negative 1 is a negative number. This number negative 1 used as x makes 8 minus x a positive number. Okay, now just like the question we did a moment ago, which was 7 to the 5x minus 3 is equal to 4, here we're going to use the same kind of logic because one side of log base 3 of 8 minus x equals 2 was a constant, namely the right side, which was just the constant 2. The definition of logarithm was useful, just like when we solved the equation up here. Or again, one side was constant. So if you have a constant on one side, and the other side is either exponential or is logarithmic, the definitional logarithm is helpful. Now let's solve 3 to the 4x minus 1 equals 7 to the power 5x minus 2. Here, unlike the first question we started the day with, it doesn't make sense to try to turn 7 into 3 to the something power. So let's apply the natural logarithm to both sides. So ln of 3 to the power 4x minus 1 equals ln of 7 to the 5x minus 2. Why is applying a logarithm of whatever base you choose, but ln is just the easiest to use. Why is applying a logarithm of the same base to both sides helpful? Well, because we can use a law of logarithms. So using the third law of logarithms, we have 4x minus 1 times ln of 3. Now, because 4x minus 1 consists of two terms, we need to write this in parentheses. If you didn't write the parentheses, this would mean something else. Yeah. Same deal on the right side. Quantity 5x minus 2 close parentheses times ln of 7. Now we can distribute. So you can distribute ln of 3. So you have 4 times x times ln of 3 minus 1 times ln of 3, which is just ln of 3. On the right side, distribute ln of 7, and you have 5 times x times ln of 7 minus 2 times ln of 7. So the comment here is that ln of 3 distributes. Ln of 3, after all, is just a number. Ln of 3 is the same as log base e of 3. In other words, e to the what number equals 3. So we're distributing the number ln of 7. Ln itself, the function, does not distribute. Okay, so got to be very careful with what's going on here. Ln of 3 is a number and therefore distributes. Ln, the function, doesn't. Okay, and then we can reorganize some things here. We can subtract 5x times ln of 7 on both sides. We can add ln of 3 to both sides, and we have this. The purpose of the structure of this is we got all the terms that have x on the left side and all the terms that don't have x on the right side. So why would we want all terms that have x on one side? This goes back to an old technique from a long, long time ago. That when you have all the terms that have the variable on one side, like here, all the terms that have the variable x are on the left side, you can factor out an x. So we didn't do anything to the right side. We didn't do anything to both sides. All we did was we rewrote the left side by factoring out x. So we have x times the quantity, 4 times ln of 3 minus 5 times ln of 7. Now, the great thing about this is that the previous line had two written copies of the variable, and now the new line that we have here has only one written copy of the variable. We have x times some stuff in parentheses, and we can divide by what's in parentheses on both sides. So if x equals the fraction ln of 3 minus 2 times ln of 7 all over 4 times ln of 3 minus 5 times ln of 7. Now, I know this looks messy, but we're done. And in the fraction, do the ln of 3's cancel? No, they don't, because of the minus sign, right? They're not factors. Similarly, the ln of 7's don't cancel, okay, due to the minus signs. Okay, just going back to the thing we said here, ln of 3 is a number. Remember, it's really the answer to the question 3 to the what equal, sorry, e to the what equals 3. So ln of 3 is a number and therefore distributes. Right? The work here is the same as if you had 4x minus 1 in parentheses times whatever, like 25, right? So ln of 3 is a number and distributes, but ln is a function and does not distribute or factor. Okay, ln is a function. You can't factor out the function. That doesn't make any sense. Okay, you can't distribute the function. But ln of 3 is a number and distributes. Okay, let's look at 3 to the 4x minus 1 equals 9 to the 5x minus 2. Now, we could apply ln to both sides, like this, and then go ahead and, using the third law of logarithms, bring the 4x minus 1 in front, the 5x minus 2 in front. Think again about why we need parentheses around the 4x minus 1. It's due to the order of operations. If these parentheses weren't here, the left side would say something totally different. Now the work follows just like the previous problem. In fact, the question was just like the previous problem. It's just the 9 that's there. Let me just go back a slide. It was just where the 7 was. So all the places you see a 7 here, if you instead replace with a 9, the work follows just like the previous question. That's one way to make an answer, but it's actually, if it go back previous slide, it's actually a very long-winded answer. And here in this question, you had to do it this way because 3 and 7, well, there's really nothing in common there. But for this problem, there's actually a much nicer approach. Just much less writing is involved if you replace the 9 with 3 to the second. Then you can multiply the exponents using the exponent law that we had from way back when. So I went ahead and already distributed the 2. So I could have written 2 times quantity 5x minus 2 as the exponent. I just went ahead and wrote 10x minus 4. But now the point is we have the same base. Right? The original question we didn't, which is why we had to do some work. But now that we have the same base, we can set the exponents equal. And the rest of the work is fairly routine here, so we won't complete it. But the point is, if you look at answer 1 versus answer 2, haven't finished either of them, but I hope you can see that answer 2 is going to be a lot less writing. So it's going to take less time, it's going to be less tedious. We don't always get to do it the second way, but we're lucky because 3 and 9, well, we can write 9 as 3 to the second. So if the bases seem related, there's no need to apply the logarithm to both sides. There's no need to apply the natural logarithm function to both sides. That method would work, it's just more time consuming. And so there's that, think of it like a bigger hammer, and you have that tool available if you need it. And when should you use it? When you have to. If the bases seem unrelated, apply ln to both sides. So consider the following 4 equations to solve. What's the first step to the fastest method, or in some cases the only method? So 4 to the 5x minus 8 equals 32 to the 7x plus 3. Second equation is 7 to the 5x minus 8 equals 13 to the 7x plus 3. Third equation is 7 to the 5x minus 8 equals 14 to the 7x plus 3. And the fourth equation here is 3 to the 5x minus 8 equals 81 to the 7x plus 3. So what do you think a first step for each of these should be? Well, for all 4 of these equations, you could certainly apply ln to both sides. And there are some equations where that's really the only approach. But for some of these, there's faster approaches. So the first equation, both 4 and 32 are powers of 2, right? So you could replace the 4 with 2 to the 2. You can replace 32 with 2 to the 5. For the last equation, 3, just leave it alone, but then 81 is 3 to the 4th. Okay? For the second and third equation, the most natural thing to do is apply ln to both sides. So let's talk about some of these things. You could apply ln to both sides of the first equation and the last equation. That's fine, you can do it that way, but it ends up being more writing. It's just a lot more writing. So it's faster to notice that both 4 and 32 are powers of 2, and both 3 and 81 are powers of 3. Now, for the third equation, don't let the fact that there's a 7 and a 14 throw you off. Yeah, I picked this very intentionally. 14 is double 7, right? 14 is in fact 7 times 2. Yeah, 14 equals 7 times 2. But 14 isn't a power of 7. We don't write 14 as 7 to the something. For instance, 14 isn't 7 to the 2. 14 is 7 times 2. 7 to the 2 is different from 7 times 2. So 7 times 2 is 14, yeah. 7 to the 2 is 49, which just didn't appear in the problem. If question 3 had different problem, been 7 to the 5x minus 8 equals 49 to the 7x plus 3, then we would have replaced the 4. Okay, if there were a 49 here, we would have replaced 49 with 7 to the 2, but that's not what we have. We have 14. So don't let that throw you off. Yeah, I would treat the second question and third question in the same way. The fact that 14 is equal to 7 times 2 isn't really all that helpful here for this problem.